left off last time was doing binary and hexadecimal encoding of positive integers or zero. Okay, we'll continue with that at the very beginning, and then we'll also start to talk about basically how do you deal with negatives, because it's not the way you'd think. Okay, so let's just pick a couple of numbers sort of completely at random here. So let's pick 42 and somebody give me another number.
97.
97, okay. Thank you for not picking the other number that I'm sure everybody was thinking about. So, yeah. All right, so let's encode these as 8-bit unsigned binary numbers, okay? And so when I say unsigned, what I mean is this. So a uint 8 is an 8-bit unsigned integer, the U for unsigned, okay, and can encode 0 through 255. Okay, in hex that would be 00 through FF, right? All 255 patterns. So, or 256 patterns, right? So it's 256 total patterns, but the biggest thing you can encode is only 255 because we have to spend one of the encodings on 0. Okay? And not shockingly, what's the encoding of 0? Just all zeros. Okay? So that one's easy. Okay. Now, if you use more bits, then you can encode bigger numbers or more numbers. And for the purposes of at least doing this on paper, like if you can do it for 8 bits, you can do it for 32 bits. It's the same deal, just more bits, okay? So we'll kind of restrict our attention for the most part to 8 bits just for kind of convenience. But 32 bits, 64-bit, it works the same way. It's just more bits. Okay, so if I want to encode these two numbers, then let's start by doing our 2 to the 0, which is our ones place. So let's just write down all the places. Oops. Okay, so these would be the 8 possible place values for our 8-bit number. And again, if it were a larger number of bits, you would just keep going. Okay, so let's take our first number, 42. Can 128 fit into 42? No. So what am I going to put in this pot?
0.
A 0, right? Same thing, 64 can't fit into 42, so I'll put a 0 there. Okay. Can 32 fit into 42?
Yes.
Yes, once, with 10 left over. Can 16 fit into 10?
No.
Can 8 fit into 10?
Yes.
With 1 left, or 2 left over? Can 4 fit into that?
No.
Nope. Can 2 fit into the leftover 2?
Yes.
Yep, and then there's no leftover and we're done. Okay, so 42 as a base 10 number is equal to the binary number 00101010. And if we wrote that in hex, it would be what? So take it 4 at a time. What's the left 4? 0010, that's 2. And what's the right one? It's an 8 and a 2 is 10, which is A. Okay, so 0x2A is hexadecimal. Okay, so good? All right, now, you guys do the same thing for 97. And I'll play the Jeopardy music up here, and we'll see what you get.
Is that 0B00?
Yes. Yeah.
Oh, right, because
To indicate that it's in binary.
Okay. Yeah, yeah.
so, like I said, I'll sit up here and play the Jeopardy music, yes.
I have figured this out.
Oh, well, une minute, s'il vous plaît. All right, so what'd you get for the binary? Thomas, go ahead.
011-00001.
Agreement, disagreement from the peanut gallery? Yeah, okay, what about the hexadecimal? 6-1, yeah. Okay, peanut gallery agrees? Yeah, excellent. All right, so the next thing, let's actually add these two numbers. And first off, let's just do it like elementary school style. 2 and 7 makes 9. 4 and 9 makes 113, 139. Okay, so how would we do this addition process if we were doing it in binary and not base 10? Okay, so first off, let me write down the two numbers again. Okay, so I'm just writing down the binary that you guys, that we got earlier. Okay, and this process works exactly the same as it did in grade school, but you have 2 fingers instead of 10. Okay, so what is 0 plus 1 in the first, in this place? 1. Okay, what are the 4 possibilities that we could have had there? We could have had 0 plus 0, which is 0. Okay, that's easy. 1 plus 0, which is 1. Yeah, wake up. All right, 1 plus 0 or 0 plus 1, either way, would have given us a 1. And then the fun one is, what's 1 plus 1? 0 carry a 1. Okay, so it's the same thing that you would do if you had like 6 plus 4, okay, in grade school, 0 carry a 1 to the next position. Okay, okay, and in this particular number, we don't have any carrying until here. So in that place, what's 1 plus 1? 0 carry a 1. 1 plus 1 is 0 carry a 1, and we get a 1. Okay, now let's double check that this is in fact 139. Okay, and how do we do that? The first one, so this is 128 plus no 64, no 32, no 16, 1 8, no 4s, 1 2, and 1 1. Does that add up to 139?
Yep.
Yeah, last time I checked. Okay, so it worked. Okay, good. So addition works exactly the same way it did in grade school with one exception. Okay, so let me take 139 and add it to itself. Okay, just treat it like it's the original problem was just to do 139 plus 139. Okay, so 139 in binary was, what did we get? 1000, 1011, and then I'll have the exact same thing below. Okay, 1's position. Sum is 0 with a carry. Okay, and then now look what I've got. I've got 1 plus 1 plus 1 is 1 with a carry. Okay, so let's think about why that is. So this would be like the situation, let's say you had 7 plus 5. You get 2 with the carry, right? So the sum could still be a non-zero digit, and you have a carry. Okay, except in this case, what's the only sums that you can get? 0 or 1, that's it. Okay, so this one is 1 with a carry. Okay, do you guys accept that one? Okay, all right, and then now we just continue. So 1, no carry, 0 with a carry, 1, no carry, 0, 0, and then here's something interesting happens. Okay, 0, and what do I need to do? Carry a 1 to the 9th position. Okay, now this is where computer arithmetic and human arithmetic diverge. Okay, if I say in advance that there shall be 8 bits for our number, and I just got what looks like a 9th bit, where does that 9th bit go? Nowhere. It just disappears, and the sum is this. Okay, so the 9th bit well, it would help if I could spell this morning. Okay, this is called overflow. Okay, and this is the situation that I kind of alluded to at the end of class last time when we were talking about the clock, right? So we said, okay, humor me for a moment and let's pretend that instead of 12, it's 0. Okay, so we've got 0 through 11 on the clock. What's 6 plus 7 on the clock? 1. It cycles back around, okay? So you might say 6 plus 7 is 13, right? But there is no 13. It just vanishes, okay? So that's called overflow. Now looking at the binary number that we got that I've circled in blue, what does that represent? Okay, so what is this? Well, we've got a 2 and a 4, that's 6. And then we've got an 8, or no, sorry, a 16. All right, so this is 22 in base 10. Yeah? Okay, now let me convince you. So what it looks like is 139 plus itself is equal to 22. And you guys are like, wait a minute, I thought you were a mathematician. You're telling me 139 times 1, or plus 139 is 22, right? Okay, so what's the actual answer like if we were to do this grade stool style? Huh? 278. Okay, so we were expecting 278. We got 22. Okay, now what I want you to notice is that 278 is 256 plus 22. Okay, so on the clock example, we did everything sort of in units of or groups of 12. Okay, and anytime you went above 11, you cycled back around to 0. This 8-bit scheme is equivalent to a clock that would have 256 different positions, 0 through 255. Okay, so in some sense, the number 278 and the number 22 are the same. Okay, now, has anybody ever seen modular arithmetic before? Okay, that's the system we're really working in, is mod 256. Okay, if you don't know what that means, become a math major. Awesome. Okay, so would you guys agree that this is a problem, what just happened? Yes, okay. Now, what this says then is, okay, maybe it's not such a great idea to restrict ourselves just to 8 bits, okay? Why don't we use more bits? Okay, well, let's say we used 32 bits. Could this overflow problem still happen? Yes, it happened to YouTube, as we talked about, okay? So it doesn't matter how many bits you use, this overflow problem still can happen. It's just less likely to happen because the numbers get so huge, okay? The 8-bit scheme, while convenient for paper, sort of exaggerates the importance of it, okay? Now, this, by the way, was how computers were capable of doing arithmetic in the 1980s. So your personal computer in the 1980s, so like my Commodore that I think I showed you guys, could do 8-bit arithmetic, and that was it. Now, it could do, I've kind of lied a little bit here. That 9th bit that disappeared, there was a special place to put it. That wasn't part of the 8 bits. It was sort of like a, well, it was called a status register. But basically, it would just tell you, hey, bro, an overflow just occurred. So you could make decisions based on that. And that allows you to do actually more arithmetic than you seemingly could otherwise. Okay, but that's kind of a technical point. Yeah, okay, good. So the answer you may get may be surprising, but what will be the case is that the answers will have the same remainder upon division by 256. Okay, so what's the remainder of 22 when you divide it by 256? Well, 22, right? 256 can go into that. And what's the remainder of 278 over 256? 22, same thing. Okay, so they have the same remainder, and that's really what means they're the same in our kind of clocky looking system. Okay, does that make sense? Okay, so next we want to talk about how do we deal with negative numbers. Okay, and this is why I have to say in advance whether or not I'm using an unsigned system or a signed system, because they look slightly different. Okay, now, so we good? Can I go on to a clean sheet? All right, I promised you guys a magic trick. Okay, so what were the two numbers we had a minute ago? 42 and 97. Okay, so let me do 97 minus 42. Okay, and I'm just subtracting the 42 from the 97 because it's smaller, and that'll make explaining the answer more simple in this case. All right, so how would I have done this in grade school? Well, 2 from 7 is 5, 4 from 9 is 5, no big deal, 55. Okay, yes? Okay, let me do it with my magic trick. All right, so my magic trick requires us to do this. There are 10 digits, 0 through 9, okay? And I'm gonna pair them up. I'm gonna pair 0 with 9, 1 with 8, 2 with 7, 3 with 6, and 4 with 5. Okay? So I've paired them up. Okay, so let's take 42. Okay, and what I'm going to do is I'm going to write, instead of the 4 and the 2, I'm going to write their mirrored pairs in this crazy scheme I've come up with. Okay, so what does 4 become? 5. And what does 2 become? 7. Okay? All right, add 1 to that. You get 5, 8 now. Yeah? All right, now let me take 97 and 5, 8, this sort of mirrored version with an extra 1 thrown in. Add those. Well, what's 7 and 8? 15, carry a 1. What's 1, 9, and 5? 5, carry a 1. Discard that carry, and look what I got. Huh? I got 55. And I did it without doing any subtraction. Okay? You could. And in fact, guess how subtraction works on the computer? It's like this. Okay? So, unlike a good magician, I'll reveal my secret. Okay, I could prove to you why this worked. I won't. I'll let you stew in mystery for at least a little bit. Okay, but I could, right? I could reveal my secret. Okay, so it looks like magic, right? Maybe it's not. It's math. It's math and magic. Right? Okay, so what I have done here is called computing the tens complement of a number. Okay, so the number 5, 8 is the tens complement of the number 4, 2. Okay, it's the mirrored pairs or mirrored number plus 1. Okay, and the nines complement is what it's called before I added the 1. Okay, so what I did was I wrote down the nines complement, added 1, and that gave me the thing called the tens complement. Okay, now the way that we'll do this in binary is exactly the same, except it's the 2's complement and 1's complement instead of 9 and 10, because, well, we've only got 2 bits. Okay, now here's the fun thing. When I paired up the numbers, or the digits, I had 5 different pairs, right? 0 and 9, 1 and 8, 2 and 7, 3 and 6, 4 and 5. Because I had 5 pairs because I had 10 digits. Yes? In binary, how many digits or bits do we have? 2. So there's only 1 pair. You just switch them. Okay? Yeah. So, all right. So what did we get for 42 in binary? What was it?
00101010.
Oops. Okay. So that was our binary representation of 42. Okay. What I want to do is say, okay, well then therefore what is the binary representation of minus 42? Okay. So let's do this. First step, flip all the bits. Okay, so that's like mirroring 0 became 9, 1 became 8, and so on in my magic trick. Okay, so I just flipped all of them. I'm going to add 1 to that. Okay, and this is going to require a little bit of work. And do you guys agree we get this? Okay, so this represents negative 42 as an int 8. Okay? Now, if you looked at this from what we did 10 minutes ago, you might think that this represents something else. Okay? And this is why it's so critical that we specify in advance, are we dealing with the unsigned version or the signed version? Okay? So if you think about this, right, I've got 8 bits written down in here. Those 8 bits can represent numbers. They could even represent letters. They could represent parts of a sound. They could represent anything, right? And I have to decide in advance or specify in advance what kind of data this is and what encoding scheme I've used for you to be able to decode it. Because otherwise it's just a jumble of 1s and 0s and you don't know what the hell it is. Okay? So, if we had done this 15 minutes ago, what would this binary number represent as an unsigned version? Okay, so forget any of this negative nonsense. So sit down and compute that for a moment, please. See you play. And then I'll go through the computation. Yes?
Can you repeat what you asked?
Yes, okay. So, I claim that this represents minus 42. Okay, and I'll demonstrate why it does in a minute. But, let's say that we hadn't talked about any of the negatives. I just have this binary number. Okay, so in the same way that when we encoded 97 and stuff earlier, we've got a binary number. What does this represent if I don't worry about the minuses or anything? Okay, got it? And then I'll demonstrate the computation that we'll be doing. Okay, so as sorry. Okay, so it would represent 128 plus 64 plus 16 plus 4 plus 2, because those are the positions that the ones are in. Okay, and what does that all add up to? 214. Okay, great. Okay, so what I want you to notice is that negative 42, oops. Negative 42 and 256 add up to 214. Right? What's so special about the number 256? Well, it's 2 to the 8th, and we're using 8 bits. Okay? So in our clock arithmetic, negative 42 and 214 are the same thing. Okay? Or they look the same. Okay, so this is why, like I said, it's critical that we specify in advance, am I working in the positives and negatives version or just the positives version? Okay, and the distinction, the label for this that I'll try to use is int 8 means signed. That means negatives could be possible. uint 8 means unsigned, hence the U, okay, in which case there are no negatives, okay? So if I handed you this binary pattern and I said, okay, what is it as a uint 8? It would be 214. As an int 8, it's minus 42. Okay, so same bit pattern represents two different things. Just depends on which system. Yeah.
I didn't catch that. So int 8 is signed or unit 8 is not?
Int 8 is signed. Uint 8, the U is for unsigned.
Gotcha.
Okay.
So if it's U or int 8, so if it's signed, will it always be negative?
No, not necessarily. Okay. So the signed system, this example turned out to be negative. Okay. And in fact, the way that you can tell in a signed system whether or not the number is negative is look at the far left bit. If it's a 1, it's negative, otherwise it's positive. Okay, so that's a quick way to just look at it. Okay. Now, I haven't actually demonstrated that this number really ought to be minus 42. Okay? How could I test whether or not, like, you guys just are trusting me that this binary pattern really is minus 42? Okay, but how do you know I'm not just pulling this out of thin air or some body part? Digestive organ, right? Yeah, well, the excretion organ, okay? How do you know I'm not making it up? Yeah, how could I test it?
By trying to add it to another binary number.
Yeah, so, and what would be a really good number to test this against? Well, how about 42? Because what should happen if I add 42 to negative 42? I damn well better get 0. Okay, and if I don't, then something has horribly gone wrong. Okay? All right, so let's do that. Okay, so what did we get for 42 again? It was
00101012.
okay, and negative 42 we just got my number, the thing I claimed, was this, right? So I'm going to add them together. And I damn well had better get 0. Okay, 0 and 0 is 0, good. 1 and 1 makes 0, carry. 0, carry, 0, carry, 0, carry, 0, carry, 0, carry, 0, carry to the 9th position, but what happens to him? Disappears, and lo and behold, I did in fact get 0. Okay, so my magic trick worked. Isn't this devious? Yeah. Okay, so this system that we're using here, this method, is called the 2's complement. Okay, and that's how we deal with negatives in on computers, or negative integers. Floating point's a whole other bag of hurt. Okay, so an uint 8, which is where we started. What's the smallest number you can represent with a uint 8? 0. Okay, sounds good. What's the biggest number we said we could represent? 255, right? For a total of 256 numbers. And if with 8 bits, what's 2 to the 8th? 256, so that's why it's 256 things. As an int 8, okay, so including the sign, what's the smallest number we can represent? Yeah, negative 128. And this goes up to 127. And that would help if I could write this morning. Okay, how many things is that? Still 256 things, but now we have the negatives involved, or at least some of them, right? So we got some positives, we got some negatives. Okay. All right, so the trick here is that if I want to do subtraction, I don't actually do subtraction. I add the negative, right? So this mirroring trick, when I did it with the base 10 number, okay, or when we did it in binary, rather than actually doing the subtraction like I might have in grade school, I said, no, let's do my magic trick instead. We'll compute, all right, what's the negative of the thing I want to, that I've got, and add that instead, okay? Because isn't something plus negative 42 the same as that thing minus 42? Right, those mean the same thing algebraically, and so I'm free to do whichever one I want, and I claim that it's easier to compute this. Okay. Now. Okay. So is it okay? I know your minds are kind of right. It's like that meme of like the dude in the black turtleneck, you know, from like the 80s or whatever, and there's like the, you know, swirling stuff coming off of his head. Yeah. I feel like I need like another screen right here with like memes, and I'd have like a meme button deck just to spice things up. Yeah. Okay. Hey, you could, right? Okay, so the next thing I want to talk about is kind of something I alluded to at the end last time, okay, which is that this system of doing arithmetic, okay, is a little weird, and like it was, like I've been using the clock as our example, it's more like a clock with 256 different positions than it is the arithmetic you're used to, okay? So, what number added to itself gives you 0? Well, 0 certainly works, right? 0 plus 0 ought to be 0. Right? Is there a second answer to that question? Huh? Okay, 128 or minus 128, depending on whether or not you're working in the unsigned or signed system. Okay. Okay. Okay, so let's think about that. In the unsigned system, what's 128 plus 128? 256. Can you represent 256 in 8 bits? No. It would be a ninth bit that's a 1 followed by 8 zeros. And what happens to that ninth bit? Poof, overflow. Okay? In the in the signed system, the answer is minus 128. Okay? And the reason there is what's negative 128 plus negative 128? Negative 256, same problem. Okay? So I'll demonstrate that in a moment for negative 128 because it's kind of interesting how that ends up working. All right, now do we agree that 0 definitely has that property? Right? That's obvious. It's whether or not there's a second answer that's not so obvious. Okay, so let's take minus 128, okay, and negative 128 as a uint 8 is 1 followed by all zeros. This, by the way, oh, I'm sorry, I'm in an int 8. It just so happens that their encodings are the same, okay? So if I have 1 followed by all zeros, signed that represents negative 128, but unsigned it represents 128, okay? Okay, now for right this instant, you guys are looking at it and being like, how does that represent minus 128, okay? Let's say that I don't know what it represents, okay? How could I figure out what it represents? Well, could I do this trick of flipping all the bits and adding 1? Okay, that's equivalent to negating the answer, right? So if I have a bit pattern that I say is negative 5, and I flip all the bits and I add 1 and I get the bit pattern for 5, then are you convinced that what you started with was minus 5? Yeah, okay, so that's worked. So let's do that. Let me take 1 0 0 0 0 0 0 0 and flip, and so I get, and I'm going to add 1. Right, so this is the magic trick. Oops. I get that. You guys agree? Oh, that's interesting. What did I get? The exact same thing back. Right? And so this question, like if I asked a bunch of middle schoolers what number added to itself gives you 0, they'd say 0, and if you told them that there was a second answer to the question, they'd laugh you out of the room. Okay? But we're not working in the same arithmetic system, so there is a second answer. Phone's busy. Sorry. They can't answer. It's too early to order a pizza. Okay, good? So, mind's blown? Sort of? Okay, so we've done this with 8 bits. The exact same scheme works no matter what number of bits you pick, okay? Like I said, for convenience, we'll work with the 8-bit scheme simply because it's less crap to write down. Excuse me, even though in modern computing, you almost never use just 8 bits for anything. Okay? It's just too small to represent much. Okay? So, what's the big danger, though, that can happen when you're doing this is overflow. Okay? It will happen. Okay? It's going to happen. And it's how you deal with that overflow and being cognizant that it could happen that are critical, okay? Now, Friday next week, we're actually gonna read and do something very different than what we've been doing, which is you guys are gonna read stuff and we're actually gonna kind of discuss some papers, okay? We're gonna do that a few times throughout the semester, but the stuff that we're gonna talk about on Friday next week is about how overflow errors like this have killed people, okay? Or almost killed people, or cost billions of dollars, okay? So you have to be cognizant that this can and will happen and design like a program with that in mind, okay? And even the people that worked for Google, for YouTube, right, even they screwed this up. And would we agree that the people that work for YouTube are probably pretty damn smart? We hope so, right? Now, did anybody die when the Gangnam Style video issue, that overflow, killed YouTube? Or, sorry, broke YouTube? Right? That didn't kill anybody, right? But there have been situations where things have blown up or people have died because of somebody not taking into account these errors, okay? Or other kinds of computer arithmetic precision issues, which the other one we'll have to talk about when we talk about floating point, which we'll start on Friday, okay? So, yeah, one of the other examples that I'll mention is these overflow errors also occurred with early software for the Boeing 787. Anybody flown on one? Dreamliner? That's a sweet plane. It's a real comfy ride, especially if you're up front in first class. Kind of sucks if you're back with the cattle in the back, but yeah, first class. Right? What's the Fergie song? Right? Flying first class up in the sky, drinking champagne. No. No. Okay. Anyway, if I continue, I'll probably get a copyright strike and a bad singing strike on Twitch and YouTube. Right? Okay. So yeah, the 787 had this problem. The first launch of the Ariane 5 rocket by the European Space Agency in the 90s blew up about a minute after launch because of an overflow error, right? Or it just started, went wildly off course, and so they detonated it for range safety. And those didn't kill anybody, okay? The one that killed people was in the first Gulf War in the early 90s, the Patriot missile system. It turned out, this is so crazy, that the computer, the precision that it could calculate things got worse the longer the computer had been turned on. Okay, odd problem, but it's a problem. And so this particular Patriot missile battery had been turned on for so long that it was no longer able to precisely enough calculate the trajectory of an incoming Scud missile from the Iraqis, and failed to shoot it down. And the missile hit a barracks and killed like 30 people, 30 servicemen. Right? I think we could agree that that was a bad thing. Yeah. Okay. So anyway, so we'll talk about some of those things. Okay, but okay, so just kind of to recap then, right? We've got the signed and unsigned system. Okay, and the brilliant part about the signed system is that rather than actually doing subtraction, we can do addition, but with a negative. Okay, so this process, the magic trick of flipping the bits and adding 1, that is equivalent to computing the negative of a given number. Right? So if I know the representation of 42, by doing this magic trick, I get the representation of minus 42. Okay? Now, there are 2 numbers for which that doesn't work. 0, but do you really need to compute the negative of 0? well, it's 0, right? You don't need to think of it, but it's obvious, okay? So that one's no big deal. But the other one that's weird is minus 128, okay? Because what happened when we did this flippy procedure? We got the exact same thing back, okay? Those are the only two numbers for which that'll happen, okay? 0 and minus 128, which is special. We call it the most negative number, okay? It's the most negative number representable with an 8-bit scheme. Okay? Now, 32-bit number, what's the most negative number? It's like negative 2 point something billion, right? Whatever that is. Okay? But there's always two of these bit patterns that have this property. All zeros and 1 followed by all zeros. Okay? All right, now, let me just point out a couple of things, misconceptions that I've seen students have over the years to make sure that you guys don't do them. Okay? The first is to think that all this 1 in the front does is tell you the sign. Okay? It does tell you the sign. In a sign system, if this bit is a 1, you know you have a negative. Okay? But let's say that I had this bit pattern. Okay? What would be the trap to think of this number as being? Negative 1. Okay? That's not how the system works. So you can't say, oh, this right-hand 7 bits, that's 1, and it's got a 1 in the front, so it should be minus 1. That's not the way this works. Could we have done the system that way? Yes, but we don't. Okay? And here's a good reason why. If that were the case, what would this number be? 1 followed by all zeros. Negative 0. Well, what the hell does that mean? Right? It doesn't make sense. Okay? So we could have done the scheme that way, but that would have been the problem. We'd have two different ways to represent 0, and that's kind of bizarro. Okay? So that's not correct. Okay? So if you've got a number that you know is negative, okay, how do I figure out what number this is? I flip the bits and I add 1. I decode what I've got, and then I know the answer to my question. Okay? And it turns out, and I'll let you guys do this on your own just to trust me, I'm a doctor, this is actually minus 127. Okay? Which, if you think about it, actually kind of makes sense. What you're doing is counting up from minus 128 instead of counting up from 0. Okay? All right, so that's misconception number 1. What was misconception number 2? Oh, the flipping. Okay, so when I say flip the bits, what do I mean? Each bit gets mirrored, right? So I'm not flipping like this way or whatever, right? I'm mirroring each individual bit by itself. Okay, because I have had a few people that are like, oh, well, if you flip the bits, then that would just be 7 zeros and then a 1 at the end. You flipped them. Okay, that's not what I mean when I say flip. Okay, I mean the flipping is in my magic trick. Okay, so this is kind of starting to make sense. Okay, you guys will have to practice this, which is of course where the lovely Canvas assignments come from. You get a Canvas assignment, and you get a Canvas assignment. And yeah? Okay. All right. So I'll post some of that stuff, and then also the details for the last circuit thing that you guys will do. And Friday next week, we're going to do 2 things. First, we're going to kind of have a discussion for most of the class about some of these readings that I'll post for you guys. And the second is the president's henchman, Jim Amidon, if any of you guys know him. So apparently Friday next week there's going to be a bunch of like video people here, and they want to get like some video stock footage of students doing cool stuff. And so naturally he asked me, right, if I would volunteer my class to do cool stuff on camera. And so we'll have you guys sort of demonstrating the final circuit project for about 10 or 15 minutes so we can get some good video. guys on Friday.